Welcome everybody to the session. Today we're going to talk about time series with SQL Server 2022. My name is Gianluca Sartori. I am the founder at Quantum Datis. We're a small consulting company in Italy. I'm a data platform MVP. I've been doing this kind of things for a very long time. I started with version 7 back in 1998. So that's a long time ago, which also means I'm old. Currently, I'm working as a DBA at a famous Formula One team in Italy, the one with the red cars and the prancing horse. And if you want to read my blog, you can find it at spaghettidba.com. I'm not writing there very often, but the blog is there. And if you want to follow me on Twitter, my handle there is at spaghettidba. Okay, cool. So what are we discussing today? We're going to have a look at what is time series data, what is all about this data that we call time series data. We will see that it is a bit different from we are used to working with. It is different from relational data, so it has to be treated properly. And usually, treating this data properly means you are not using a relational database. So we're going to go and have a look at what is available on the market for time series data. And we will also use one of the databases in the market, probably the most popular one in the market, which is called InfluxDB, as a mean of comparison for what we have in SQL Server. And we will see what we need from a time series database, and we will try to find out whether what we have in SQL Server, and in particular SQL Server 2022, is acceptable to work with time series data. Basically, the problems that we will have to solve have to do with storing the data. It's usually a lot of data, so it has to be stored properly. And we will also deal with the other problems that are typical to time series. So handling retention policies and downsampling, and querying the time series data, which has a particular pattern, usually comes in particular patterns of querying. Good, so first of all, definitions. Let's get that out of the way. So what is time series data? It is data that, unsurprisingly, comes with a time attribute. So every time we're dealing with data that always comes with a time dimension, that is time series data. So this usually comes from performing observations of an object, of an entity we want to observe, and we repeat these observations over time. There's probably a thermometer in this room. If I walked to the thermometer and read the temperature from that, I could write down that number, that temperature, also noting down the time when the observation was carried. And that is what we have when we are dealing with time series data. And of course, a time series database is a database designed specifically for dealing with time series data. So it is optimized for this type of problems. So it has built-in optimizations as it is built from the ground up for this. Good, so this is something that is found in many possible applications. This could be, as we said, something that comes from observing an object that comes from the real world. So a temperature, we can observe that using a simple thermometer. But this could also be an observation on something that is immaterial, like stock prices or things like that don't really have a physical concept in the real world. So every time we perform an observation of a stock prices, we note down the price and the time. But this could also come from an IT world type of source, like, let's say, a performance counter. We are probably, most of us are people coming from SQL Server, so using performance counter is something very typical of what we do. So we could note down the values for some performance counters and the time when this observation was performed. So we could have the CPU percent or how many emails per second and stuff like that. And obviously, there is the whole world that comes from sensor data. Nowadays, pretty much everything is instrumented and has the ability to emit some performance data, some telemetry. And this telemetry is made of numbers, of observations of things that will emit some numbers and a timestamp attached to that number. So just to make a very typical example coming from the SQL Server world, we could be measuring the CPU performance over time, and what we will have here plotted usually on a chart is the series of the values we are observing, and we will have different series for different type of observations, different type of objects. So SQL Server CPU and other processes CPU in this example. Of course, we have the time dimension, and CPU usage percent is the entity that we are observing. So there are different possible ways of storing this in a time series database, but this is pretty typical of what we would find coming from performance counters. There is usually two types of time series data. Metrics, so those that come when the observations are performed at regular intervals. So all the observations are evenly spaced in time. And then we have events. These happen when they happen. So there's no timing between the observations. We just record the events when they happen, and this could be outside of any window when we perform the observations. We just capture an event, it already has its timestamp attached. Good, so how is this different from relational data? Well, relational data, we all know how this works. We have entities, and these entities are in relationships with other entities, so we have foreign keys and stuff like that. Well, none of this applies in the time series world. It is a bit different, and we will have to go and describe what are the features of time series data. So usually it is a stream of data that comes in time order. So what does this mean? When we perform an observation, that observation is for that particular timestamp when it is performed. So it is pretty reasonable to assume that the next observation will carry a timestamp that is after the timestamp of the observations that we already have performed. So the data always comes in time order. What usually happens is that we don't write our observations, our data points, one data point at a time. We usually do this in bulk. So imagine having, let's say, 1 million industrial machines that are running to perform some type of production. All these machines would upload to our centralized time series database, where we store all the telemetry at more or less at the same time. So we don't get one data point at a time, but we get multiple data points that are written in batches. The other very typical thing that happens with time series data is that we are dealing with high volumes of data. It is not uncommon to deal with billions or even trillions of data points in this space. If millions of rows is somewhat typical to relational databases, we are talking a different type of volume for time series data. So we just think of billions of data points here. Another thing that happens is that you never go back in the past to change what the observation was. We're not going back to 10 minutes ago to change what the temperature was. It was what we measured at that time. So if we want to check again what's the temperature now, we can certainly do so, but that's going to be a new observation. So that appends to the data that we already have. We never go back to change what we had in the past. When dealing with this type of volumes, what we usually do is we keep the data as long as it makes sense. So we might have high-frequency data in the short term to perform some type of troubleshooting. And given that this is a lot of data, at some point we might want to do something when the data goes out of scope. So we usually just delete it when we don't need it anymore, or we aggregate this data to keep it for a longer time. And in this case, we're not doing troubleshooting anymore. We don't need the individual data points, but we just keep an aggregation to do some type of statistics on that. Okay, cool. So why is time series data important? Obviously, if we think of how the data space has evolved, starting from the early relational databases in the 70s, we see that there has been a huge increase of the volumes of data we were dealing with. In the early 70s, what we had was the first relational databases, and we were talking about megs in that case. Then we started to work with the first data warehouses where we had terabytes of data. When the first internet online services like Google, Facebook, and so on started to appear in the 2000s, we were talking about petabytes. And now that we have telemetry and IoT and everything, pretty much everything is instrumented, we are talking about yottabytes, so incredible amounts of data that come from IoT projects. So just to give you a rough idea, we're discussing and seeing planes the whole time, so let's make an example with planes. An aircraft engine in only 30 minutes produces 10 terabytes of data. That's a lot of data. So if you think that in 2018 we had 14 million hours of flight, and each aircraft has at least 2 engines, that makes at least 560 million terabytes of data just for aircraft engines. So that's a lot of data. And this will matter more and more in the future. Okay, so the question is, should I use a relational database for this? Well, you probably know the answer already. It is doable, it is possible, but this is probably not the greatest idea. So relational databases were designed with something completely different in mind. All the things that we discussed about the features of time series data don't really apply to relational databases. If we think of SQL Server, there is no built-in storage optimization for storing time series data. We will have to figure something out ourselves. There is no easy way to enforce retention policies. When the data is not needed anymore, we will have to, well, delete it, which is probably not something that the engine likes very much. Also, querying time series data usually comes in patterns that are not extremely well received by the optimizer. So we will have to think about ways to make our queries work in an acceptable way. Well, there was at some point, and there still is, one SQL Server flavor designed specifically for time series data. So how many of you know about Azure SQL Edge? A few hands going up, okay. Has any of you done some actual work with it? Oh, one hand, okay, cool. Azure SQL Edge was designed to be, well, as the name suggests, working at the edge, so on low-powered machines to work in IoT projects. So just connected to the sensors, capture some data, store it locally for some work on the low-powered machine like a Raspberry Pi or something similar, and then upload it to a more capable database where you would store that data for a longer time. And that had some features specifically for working with time series data. And in SQL Server 2022, we got some of those features in the engine. So what we will try to find out now is whether that is enough to work with time series data or not. So let's go straight to it. And we will do that by comparing SQL Server to what is the leader in the market for time series databases to this day, which is InfluxDB. So why am I saying this is the leader? Well, I'm not saying it. There's a company that does this for a living. They just go and make ranks of what is the most popular technology in one space or another. So for time series databases, what they came up with is this list. How do they do this? Basically, they go to websites and blogs and Q&A websites and forums, and they analyze the data and analyze how many occurrences of the names that are in there. I know it's not 100% scientific as an approach, but just gives you a rough idea of how popular a technology is. And according to this methodology, InfluxDB is the most popular database in the time series space. There are, of course, other options, like Prometheus. This one is from the guys that do Grafana, which is a very popular charting and dashboarding tool for time series data. There is TimescaleDB, which is basically Postgres. And then we have other options. Of course, there are options from the big cloud players like Microsoft. There's Azure Data Explorer. Well, this was not really in the stats. I added this manually because I don't really know how popular this is compared to the other options. But of course, there are options from the big cloud vendors. So InfluxDB comes from a company based in California, which is called InfluxData. And of course, at this point, it is the most popular database in this space. It was built and optimized from the ground up for working with time series data. And much of this has to do with the storage engine that is at the core of the product. It is based on a storage engine with columnar compression and has the ability to work with retention policies, so delete the data when it goes out of scope and so on. It is written in Go. It is being rewritten right now in Rust, so there's a new release coming out soon. And it is cross-platform. Works in Windows and Linux, works on Mac. Also has the ability to work in containers, so Kubernetes and Docker and so on. Also has the ability to run in low-powered devices like Raspberry Pis and devices that can work in small IoT projects. Also, it is open source, so you can use it, you can download the code, you can change it. It is MIT, so very permissive licensing, which is also part of its success. Good, so first of all, when we want to work with InfluxDB, we have to choose which is the version that we want to work with. And currently there are three options. Well, the easiest one is to go to the guys at InfluxData and ask for a slice of their computing power. So just go to the cloud and say, okay, I need a database here. You just have to pay. You don't have to set up anything. So it's hosted as a service. This is the latest and greatest of the options from InfluxDB. So this is what is called version 3, which will be released later this year as an on-prem possibility. Well, this has been in this state for quite a while. It's been almost a year that they said it's going to be available later this year, but I will keep saying it is later this year. I don't know exactly when this will happen. So this is what is called version 3. So the third iteration of InfluxDB, the one written in Rust. This is only available in the cloud right now. Previously, we had version 2, which is also available in the on-prem, and it is the greatest version available on-prem. Version 1 is the one they started with. 1.8 is the greatest version for this flavor, and has some features that have been changed and deprecated in version 2, and then rebooted in version 3, and I suggest you start with this if you want to play with InfluxDB, because it is the easiest one to work with our relational mindset, because it accepts a language that is very similar to SQL, and some of the concepts apply there. So a database in SQL is also a database in InfluxDB, which is not the case with version 2. So we're going to discuss this in a minute. Good, so once we've chosen our poison, we're going to go and have a look at what are the design principles behind a time series database. As we said, this is a bit different from relational database. So what is the difference? Well, in relational databases, we have tables. In InfluxDB, we have measurements. What is called a column in a table in InfluxDB is called either a field or a tag in InfluxDB. A field is what contains the actual information. So let's say the temperature that I get from my thermometer. And the tags are additional properties that we attach to the observation to filter and aggregate the data. So this could be the name of the room, for example. So rooms, gate 7, sorry, just to filter or aggregate the data. A series, so, is a set of values stored in a field that we store inside a measurement. So to identify one particular value inside a measurement, we need to know, well, of course, the name of the measurement. We need to know the time. We always need to know the time to identify one particular data point. Then we need to have all the values for all the fields, for all the tags, and then the name of the field, and then we will have one single value, one data point from our InfluxDB database. So imagine doing that with the example we had at the beginning with CPU usage from a SQL Server. We will have to know the name of the measurement, so this could be CPU history. Of course, we need the time, and server name would be the tag, so let's say server 01, and CPU percent is the name of the field where we have the CPU percentage actually stored. So this identifies one particular data point. Okay, so let's make an example. Probably if you work with SQL Server, you know that there's a DMV that you can use to retrieve the CPU usage for SQL Server or other processes, and this is sysdmos string buffers. If you query that, you will have one value for SQL Server CPU and one value for other CPU every 1 minute. So we will have one at 8, one at 8.1, 8.2, and so on. If we store that in a table in SQL Server, that's very easy, but if we try to do this inside our InfluxDB database, we will have to create a measurement, and a measurement will look like this. So instead of having this stored like a table, this would actually be stored as two separate series. We will have one series for each of the fields we are storing, so SQL Server CPU and other CPU. This would be physically two separate series, and each of those will contain the time dimension for sure, and obviously the value for the field that we are storing, so the value for SQL Server CPU and for other CPU. These are two separate physical storages, and they are kept together by the logical concept of the measurement. If we throw tags in the mix, things get a bit more complicated. So for each distinct value of the tags, we will have more series. So imagine we are having server name as a tag, and we have two distinct values for this, accounting and CRM, so two different servers. Each of these will have different numbers for SQL Server CPU and other CPU at each observation. So at 1, we'll have one value for SQL Server CPU and other CPU for accounting, and two values, one for SQL Server CPU and other CPU for CRM. This means we will have 4 distinct series, so the two fields we're storing, multiplied the distinct values for the tags. So as you can imagine, the more we have distinct values for the server name in this case for the tags in general, the bigger the number of series will be, and less efficient will be the storage, because each of these will have to be stored independently. This is what we call the cardinality. So keeping the cardinality as low as possible is crucial for the successfully storing this data in InfluxDB. So how many of you know about column store indexes in SQL Server? Okay, quite a few hands up, so pretty much everyone. This is something that we also find in column store indexes. The distinct values is what really matters in column store indexes. And in fact, the storage engine from InfluxDB comes from another product, which is called Cassandra, which is a very popular column store database. What they did, basically, they started from the storage engine of Cassandra. They added the capabilities to store the data using time series attributes, and they optimized for that. But behind the scenes, it stores the data in columns instead of using rows as we would do in SQL Server. This has changed in version 3. They are using Parquet now as the backend, but this is where they started from. Okay, so imagine doing this in SQL Server. What are the options that we have available? If we store data in a table in SQL Server, we have basically two options: heaps or clustered indexes. If we store millions or billions of rows in SQL Server in a heap or in a clustered index, of course, you can imagine this doesn't really work well. It's huge in size, so it uses a lot of disk space, uses a lot of memory, and also it is hard to query. It gets very slow to query billions of rows in SQL Server in a heap or a clustered index. Also very hard to maintain. Imagine running index fragmentation or index maintenance, or just deleting some data from a database of this size. You can easily imagine that this doesn't really work well. So what are the alternatives? We need to make this smaller. Data compression doesn't really cut it, because the maximum compression, we get it from compressing by page, but doesn't really make a difference here. What we would achieve with page compression would be just inside one page, so probably divides the volume by a factor of 2, but that's not enough for us. So the alternative is to use column store indexes, and in particular clustered column store indexes. So instead of storing the data in a heap or a clustered index, we will store all the data in a clustered column store index. Everything goes only in the column store index. And this, of course, works really well, because each and every column is stored independently and compresses data very efficiently, and it is suitable for all those applications where there is a lot of repeating data. If you ever tried to work with a clustered column store indexes, you would notice that having a very low cardinality, so a very low number of distinct values, gives you impressive compression levels. So what are the downsides of working with column store indexes? As you probably know, they are not good at working with one row at a time. They like to work with data in bulk, which is exactly what we do with time series data. So it looks like a good application here. Also, column store indexes don't play well with updates and deletes. If you try to update and delete the data in a column store index, this makes the data bigger. It doesn't make it smaller. Even if you perform deletes, you also have to track the deleted rows in a separate storage. So this makes the database bigger, not smaller. Well, updates, we're not doing that because it's time series data. We only do appends. So it looks like a pretty reasonable way to treat this data. So let's try to do that. So what I have here is a database in SQL 2022 on my laptop, and it's called time series test. And what we will do is we will create a table And this will contain some data for performance counters. So we will have the name of the counter and the counter type, the instance, the object, and the value. This will be stored inside our table. So I imported some data into this table, and we're going to have a look at this data. Oh, I need to select the correct database first. Okay, so as you can see, we have this name, which is the name of the measurement, and there's the time, of course. Agent is where the data comes from. The company could be one of the attributes, and then the counter name. So you see that we have a lot of repeating data here. The counter type, this also repeats a lot, and the host, where the data comes from, this is the same on all the rows. So as you can see, there's a potential here to compress this data in a very impressive way. So let's try to do that. If we try to compress this with a clustered column store index, what we would have to do is just add a clustered column store index. What we have to do is just specify index clustered column store. We don't have to specify all the columns in here because all the columns are part of the clustered column store index. And now what we get is that all the data on all these columns is saved independently, and it is compressed at the maximum column store compression. We could also do an extra step and use data compression equals column store archive. So this takes the column store segments and compresses them even further using gzip compression. And this allows us to use even less disk space. So in some applications where the data is very huge, we could use this to reduce the footprint on disk and in memory by using some CPU. So what if we did this? What would happen here? So what we have in this database is 15 days of data for 2 SQL Server instances for performance counters for a total of 82 million rows. I know it is not a billion rows, but it's enough to get an idea of what happens. So if we try to save this in a clustered column store index, what we get, if we try to save this in a clustered index, what we get is 28 gigs of size, which is a lot. If we try to do this with a heap, it's 26 gigs. So again, a lot of disk space. But if we try to use a clustered column store index, we're down to 400 megs. So that's an impressive save of disk space and memory for this application. Using archive compression on a clustered column store index brings us down to 231 megs. So again, a huge saving in disk space. But I would like to draw your attention to this. InfluxDB manages to do this, so this is version 1, in just 91 megs. So that's pretty impressive. Like this was built from the ground up to do exactly this. So if you really want to use time series data at its maximum to save disk space, just go with something that was built for this. Okay, so this solves the problem of storing this data, but this is not done. We have more things to do. We also have to work with retention policies and downsampling. So the problem looks like this. Usually we save the data for retention policy plus infinitive, but at some point we run out of disk space. So what we need to do is decide what we want to do with the data. So at some point we will have to either delete the data or aggregate it to keep it for a longer time. So, for example, we could keep 15 days of data with a 15-second frequency, but that is good for troubleshooting. So I really want to know at that particular point in time what was the value for that performance counter. But after 15 days, I'm not doing any troubleshooting anymore. I don't need the data for that. I will keep it to have an idea of what was the usage of CPU over time just to do some stats and decide whether I need to buy new hardware, the usage is increasing over time and stuff like that. It's not troubleshooting anymore. So what I do, instead of having samples every 15 seconds, I would probably aggregate this in slices of 10 minutes and keep it, let's say, for 6 months, 2 years, whatever makes sense. So how you do it in InfluxDB is through something that is called continuous query. This is basically a query that tells, take the data from here, put it into here, and change the aggregation level from whatever it is to 10 minutes, so to the destination of this. Of course, we can achieve the same in SQL Server, but how do we do this? With jobs, probably. So retention policies is the way we do this in InfluxDB, and the concept is pretty tricky. So in SQL Server, what we have is a database, and inside a database we have schemas, and inside schemas we have tables. There's nothing like that in InfluxDB. What we have is a database, and inside it has retention policies where we save the measurements. The tricky concept is that the measurements exist in all the retention policies. You don't have to go and create them explicitly in all the retention policies. They just exist there. You only have to insert the data in the appropriate combination of measurement and retention policy. In InfluxDB2, they decided to change the things to steer the pot a bit, and what was called a database is now called an organization, which I think is a very disappointing decision, but doesn't matter. What was called a measurement is now called a bucket, and inside a bucket you have a retention period, but the concept is pretty much the same. Okay, so in SQL Edge, there was a way to say, I want to keep this data for this long, and this was called the data deletion policy. You could attach a data deletion policy to a table by doing something like this. So data deletion equals on, filter column, you decide the column that will be used to decide whether the data has to be deleted or not, and retention period equals 1 month, 1 week, 1 year, whatever makes sense in your application. So as we said, we got this in SQL Server 2022, right? No, we didn't. So if you try that in SQL Server 2022, what you get is incorrect syntax. So they probably forgot to put this particular thing in 2022, but I'm confident it will appear at some point, maybe in 2025, 26, well, whatever, doesn't matter. Anyway, not all the features didn't get ported, but it's easy. You can do that with a job, of course. Why was there in SQL Edge? Because there was no agent in Edge, so you had to set it up in something in the engine to make it work. Okay, so if we want to keep the data for a shorter period of time, how do we do this? We have to run deletes to get rid of the data we don't want to keep anymore. But of course, you can imagine that deleting millions or billions of rows is not an easy operation. Your transaction log becomes huge, and it's going to take a lot of time. So probably not the best choice to do this with straight deletes. Also, as we said, column store indexes don't like deletes. If I delete from a column store index, I'm making it bigger. So yeah, probably not a great choice. So what is probably a better idea is to use partitioning in this case. So I can partition my data by whatever makes sense to keep. So if I have a retention policy of, let's say, 1 week, I can do partitions of 1 week, and once my data is beyond the retention policy, what I simply do is switch out the partition I don't want anymore, and I just throw it away, which is a metadata only operation. So that's pretty straightforward to do without taking ages and creating billions of gigs of transaction log. Unfortunately, partitioning your data makes column store compression less efficient, because instead of storing all the distinct values in just one place, I will have to have all the distinct values for my columns in each and every partition. So that reduces the efficiency. So if we try that with partitioning, what we get is that we started from 400 megs with a column store and 231 with archive compression, and we're back to 2.6 gigs if we use partitioning. But again, it's worth paying this price if you want to do something about the retention periods. Okay, so here's the example. I can try to alter this table and add the retention period equals 1 month. So I wasn't joking, this doesn't work, sorry. But what we can do is we can use partitioning. So how we do this? We can create a partition function and we specify all the values in our range. So in this case, I'm using partitions of 1 day. And then I create a partition scheme on top of the partition function, and I add all the data to the primary file group. It doesn't really make sense here to use different file groups. And what I do to partition my data is to create my clustered column store index, not on a file group, but I do that on a partition scheme using one of the columns, so the time as a column that gets evaluated by the partition function. And for some reason, I have to specify it also on the table itself, but the index is a table itself, so it shouldn't be needed. But anyway, you have to add it in both places. Okay, so let's have a look at how the data looks once it is partitioned. If I do that, I can see that I have my data in partitions of roughly 5 million rows each. So this is a nice way to delete 5 million of rows like this with a metadata only operation. I can do that by switching out the partition when it goes out of scope. Okay, so querying time series data. That is another problem that we need to solve. There are 2 possibilities in InfluxDB. One is called InfluxQL. So this looks a bit like SQL. You see that the language elements are there. So select, from, where, group by. This is the usual stuff we deal with. And this is available in version 1 and also in version 2. And in version 3, we're going to have even better SQL support. So we already have it in the cloud. And this supports all the features in SQL standard, so even windowing functions and joins and all that kind of stuff. In InfluxQL, version 1 doesn't support joins and has a very limited support for querying. The other option is not very appealing, in my opinion. It's called Flux. This is the database that was born with version 2, and it looks a bit like Custo. How many of you know Custo? Okay, a few hands up. Do you like it? Nobody does, of course. So we had a language for querying for 50 years that worked wonders, and it was called SQL. So I would start from that if I built a product. But anyway, that's just me. Okay, so we're not going to talk about that. So InfluxQL has all the language elements that you expect to find from SQL-like language. There are a couple of things that are very useful when working with time series data. So there's group by. Well, of course, we know group by. We already have it in SQL. But you usually work by grouping by time in time series databases. And also, you have the ability to fill the slices of time, even if you don't have any data in those slices. So let's make an example. So in this case, we're querying our performance counters, and we want to group this by time 1 hour. This in InfluxDB means that we're having slices of the width of 1 hour, and the data will be aggregated inside that slice. So mean, which means average, calculates the average over slices of 1 hour. So how do we achieve this in SQL? Okay, so this is what you get. So 10 to 11 is one slice, and then one for 11, one for 12. So what we get is slices of this width. How do we do this in SQL Server? In SQL 2022, we have a new function which is called dateBucket, which is perfect for this. So what we use this function for is to create slices of the size that we specify as the first two arguments. So hours, how many? 1. And based on what? On the column that is called time. So this will create slices of this width. And we can use it for aggregating the data. So what we had in InfluxDB with the nice and easy group by time 1 hour becomes group by date bucket hour 1 time in SQL Server. So let's do an example there. So here we go. Yeah, okay. So if I run this, it's the same that I have in my slide. So date bucket hour 1 time creates slices of 1 hour. Let's start to do that. And what we get, and as you can see, we have 1 and then 2 and 3, 4. So our slices are exactly 1 hour. And we have the aggregation over this slice calculated on the counter we specified here. So lazy writes per second. Okay, so pretty straightforward. And the other thing that we had in InfluxQL is the ability to fill the slices where we don't have any data. So we say group by time 1 hour, fill now. So our slices is 1, 2, 3, and if we don't have any data for 4, that's going to be one slice that contains the value null, or whatever makes sense. So this could be fill 1, fill 0, fill whatever. How do we do the same in, yeah, here's the example. So no data for 11, what you get is a null. How do we do the same in SQL Server? We use generate series, which is basically a way to create a tally table. So the numbers from first argument to second argument. And what you get is these numbers that you can combine with dateBucket to obtain exactly the same thing that we had in InfluxQL, just a bit more convoluted. So let's try to see how this works. So generate series by itself just creates a list of numbers. So not really useful by itself, but useful, very useful when combined with other constructs. So we have our data, which is what we already have grouped by time here, and we can combine this with the intervals that are coming from generate series from our data. So what we get here is our slices of time already built. So what we have to do is just combine the two, and if we join the two things, what we get is our values. So our time slices here, and where we don't have any data, that's going to be a null. Okay. Good. So in conclusion, is SQL Server 2022 good for time series data? Well, more or less. It can work. Doesn't have all the built-in features that you find in a time series database, but you sort of can make it work. There's some manual work to do to store the data properly, to delete the data when it goes out of scope. For querying the data, you will have to write more verbose SQL, but it kind of works. It is not as efficient as a time series database built specifically for this, but there's a plus. You can store your relational data in the same database that you use for the time series data. So if you're working in a project where you need to have both types of data, you could make it work in SQL Server 2022. And the good news is you don't really need SQL Server 2022, because all the things that I showed you today, so specifically column store indexes, This has been in the product since SQL Server 2017, completely, so with support for lob data. So this has been around for quite a while. You don't really need SQL Server 2022. It's just a more complex SQL, and that's it. Okay, so if you have questions, I'm here to answer your questions, and if you want to give the feedback, this is very important for the organizers and for the speakers, so please do that. Thank you very much, and if you have questions, I'm here to help you.